Well, since we have the sum and difference identities for sine and cosine, we can quickly prove the double angle identities for them as well. Looking at the sine of 2u, that's the same as the sine of u plus u. Then we can use our sum identity for sine, that sine of u plus u is going to be sine cosine plus cosine sine. And since both of those terms are the same, the sine of 2u is double the product of sine u and cosine u. The double angle identity for cosine. Similarly, cosine of 2u is cosine of u plus u. Using the identity, we get cosine cosine, so cosine u, minus sine sine, so sine u. Or cosine squared minus sine squared. This is one identity for the cosine of 2u. There are actually a couple more. We can use the Pythagorean identities to come up with the alternate versions of the double angle identity for cosine. For instance, since we have cosine squared minus sine squared, well, sine squared is 1 minus cosine squared. When we simplify that, we'll have cosine squared minus a negative cosine is 2 cosine squared minus 1. That's the second double angle identity for cosine. The third one would be if we took that cosine squared minus sine squared and used the Pythagorean identity on cosine squared, which is 1 minus sine squared, minus the other sine squared. That will, of course, simplify to 1 minus 2 sine squared of u. So we'll have three different versions for the double angle identity for cosine. We can now use those double angle identities for cosine to help us with perfect square identities. For instance, we know that the cosine of 2u, we just showed it to be 1 minus 2 sine squared. So one thing we can do is to add that 2 sine squared over to the left side. Then we got to work on getting that sine squared alone. So the first thing I'm going to do is, of course, to subtract the cosine of 2u and then just divide both sides by 2. Which means our perfect square identity for sine is 1 minus the cosine of 2u divided by 2. We can do a similar thing for cosine squared because cosine of 2u was 2 cosine squared minus 1. So working on getting that cosine squared alone, I'm going to add 1 to the left side. And then, of course, finish it up by dividing both sides by 2. And cosine squared of u is going to be 1 plus cosine of 2u over 2. It's kind of nice to have that, those similarities between sine squared and cosine squared. That sine squared is 1 minus cosine 2u over 2, and cosine squared is 1 plus cosine of 2u over 2. That makes finding the perfect square identity for tangent squared so easy because tangent is sine over cosine. So we just substitute those two identities we just came up with. So for sine squared of u, that's 1 minus cosine of 2u over 2. And for cosine squared, it's 1 plus cosine of 2u over 2. And of course, these halves that are in each of them will end up canceling, and tangent squared is going to be 1 minus the cosine of 2u over 1 plus the cosine of 2u. That's a pretty good looking identity. Alright, so let's solve a couple equations using those double angle identities. if I have 2 cosine x plus sine of 2x is equal to 0. It would be nice to get everything in terms of sines or in terms of cosines, but I definitely have to use a double angle identity for sine. So when I do, the sine of 2x is 2 sine cosine. So 2 sine of x, cosine of x. Now, even though I don't have everything in terms of sines or in terms of cosines, I do recognize that each term has a 2 cosine in it. So I'm going to factor that 2 cosine of x out. And we'll be left with 1 plus the sine of x. Then from the zero product property, because we're multiplying these things together to equal 0, this is going to mean that either cosine of x is equal to 0 or 1 plus sine of x is equal to 0, which would mean sine of x is equal to -1. As we finish this up and we want to find all the solutions of x, we remember that we're going from 0 to 2 pi, so one trip around the circle. And when we go around the circle, there are actually 2 places where cosine is equal to 0. That's at pi over 2 and at 3 pi over 2. For sine, there's only one place where the sine of x is equal to -1, and that's going to be when x is at 3 pi over 2. So our solutions are pi over 2 and 3 pi over 2. It's just that 3 pi over 2 shows up twice. If we're going to try and solve cosine of 2x plus sine of x is equal to 0, we're going to have to use that double angle identity for cosine, and we have 3 of them to choose from. I would like to use the one that only involves sine. That way my equation will only have sines in it. So we'll have 1 minus 2 sine squared of x plus sine of x is equal to 0. This looks very quadratic to me because I have that sine squared. And when I solve quadratics, I like getting it in order first. And I mean having a positive leading coefficient. So I'm going to take that minus 2 sine squared of x and add it to bring it over to the other side. Then I'm going to subtract the sine of x to bring that over to the right side. And also subtract the 1. Now it's not too bad to factor it. Factoring 2 sine squared into 2 sine and sine, and factoring -1 into 1 and 1. Now taking a look at the sines, I want that sum in the middle to be negative sine x, which would mean I need 2 sine x times -1 to make -2 sine x, and then 1 times sine x to make a positive 1. -2 sine plus 1 sine is that negative sign that we need in the middle here. Anyway, we have a product that equals 0. That means that either one of those is going to equal 0. So 2 sine x plus 1 equals 0, which would mean sine of x is equal to -1/2. Or that sine of x minus 1 has to equal 0, which would mean sine of x is equal to 1. Now, taking a trip around the circle, all the places where sine of x is equal to -1/2. Well, sine of x is equal to 1/2 at pi over 6, and it's positive in the first and the second quadrants. So we need the pi over 6 angle that's in the third quadrant and the fourth quadrant. Pi over 6 in the third quadrant is 7 pi over 6, and in the fourth quadrant is 11 pi over 6. For sine of x is equal to 1, that happens only one spot, and that's where x is pi over 2. So here are all of our solutions. Let's also simplify a couple of expressions too. So let alpha be a position angle in quadrant 2 with sine of alpha being 2/5. And we want to simplify the sine of 2 alpha. Well, first let's kind of visualize our angle alpha. If alpha is in the second quadrant, here's alpha, and we can use this triangle to reference what the sine and cosine and tangent and everything is. We know that sine is 2/5, which means opposite over hypotenuse. Then when we run the Pythagorean theorem, 25 minus 4 leaves us with 21. And we do have to pay attention that we are in the second quadrant, so the length here is square root of 21, but because it's to the left, that value is negative root 21. Now we can go over to the identity, and sine of 2 alpha is 2 sine cosine, so 2 sine alpha cosine alpha, and we plug in the values that we know. Sine of alpha is 2/5. Cosine of alpha is going to be negative square root of 21 over 5. Then we just got to do the algebra. Multiply all this together. 2 times negative root 21 is negative 4 square root of 21. And 5 times 5 is 25. Does it make sense that this answer should be negative? Well, if you think about our angle alpha, because it's in the second quadrant, it's got to be between 90 and 180 degrees, which means when I double alpha, it's going to be between 180 and 360 degrees, making it 2 alpha being in quadrants 3 or 4. Anytime we take the sine of a value that's in quadrant 3 or 4, that value is going to be negative. And if we have that same angle and we want to find the cosine of 2 alpha, well, we don't even really need to draw it out, because the identity for cosine of 2 alpha, we have 3 of them, and one of them is 1 minus 2 times sine squared. We already know what sine is. It's 2/5. Then when we evaluate, 2/5 squared is 4 25ths. Double that means we'll be subtracting 8 25ths, and we'll need common denominators, so 1 is 25 25ths, and 25 minus 8 is 17 25ths. And there's our solution.